In this module, we will start our discussion with virtual memory. In the previous modules, we had studied caches which provide fast access to a processor's code and data. In a similar way, we will now study a technique which allows the main memory to be used as a cache for the secondary storage. And this mechanism is jointly managed by both the OS and the CPU hardware. So, virtual memory allows active portions of multiple processes to be concurrently resident in the main memory. So, as we know that multiple processes must exist together in the main memory for being executed. So, when a program is being executed, it must exist in the main memory. Now, virtual memory allows the main memory to be shared between multiple programs. Before execution, each process gets a range of virtual memory locations to address its data and code. So, as we are talking, this is virtual memory, it does not exist in practice. So, when we are compiling, when a program is being compiled, it assumes that it has a range of memory locations at its disposal. So, this is its virtual or logical address space of the program, and this can be as big as the entire addressable space of the processor. For example, in a 32-bit processor where address buses are of length 32 bits. So, the range of memory addresses that the CPU can address goes from 0 to 2 to the power 32 minus 1. So, each process in the virtual memory managed system can access as big a memory as 2 to the power 32 minus 1. So, therefore, each program or the process generates virtual addresses. Now, addresses seen by the memory unit are physical addresses. So, the virtual addresses that are generated by the CPU must be mapped to physical addresses. So, I generate a virtual address, there will be a mapping process, the memory management unit will map this virtual address into a physical address. That means, where this data that I have asked, that I have accessed will actually reside in main memory. So, that mapping will be done to that physical address, and this physical address will be floated into the memory address register of the system. And from this memory address register, this address will be floated onto the memory unit to access the data. Now, this translation from virtual addresses of a process to the physical address is done together by the CPU and OS. And what do you get additionally? This translation process also enforces protection of a program's physical address space from other programs. So, now why this is possible? We are saying that each process can address a virtual address space, can provide its code, the code and data corresponding to a process can be within its virtual address space, will be within its virtual address space. This virtual address space will be of the size from 0 to 2 to the power 32 minus 1, let us assume for a 32-bit computer, and then this virtual address will be mapped to a physical address in main memory. Now, this mapping process will be to valid locations in the physical memory where data and code corresponding to this program exists, and this mapping process or this translation process from virtual to physical address does this mapping correctly. That is this mapping from virtual address to physical address will be done only to those physical addresses which belong to this program, and it will not allow access to other portions of the physical memory where data and code corresponding to other programs reside. So, this enforces a protection of a program's physical address space from other programs. So, why is this needed? Because we said that multiple programs together exist in main memory. Now, one program should not encroach into the address space of another program. This protection is enforced by the translation process. It also isolates the operating system which is which is a separate program from other user processes. Because the operating system is protected, it conducts and nicely executes conducts all the processes happening in the entire system. So that has to be protected from user programs. OS runs in kernel mode, it has to be protected from user programs, and the translation process also ensures that user programs do not encroach into the code space of the OS in main memory. Now, the translation process also allows a single user program to exceed the size of the main memory. Because virtual address space and physical address spaces do not have a one-to-one mapping, meaning that virtual address spaces can be very big as the size of, as I said, 2 to the power 32 in a 32-bit computer, and let us say my physical address in RAM is only say 256 MB, which is much smaller. Now, the entire code, the virtual entire code and data of the process will remain in the secondary storage, and portions of the portions which are active at a given time, which is defined by something called a working set, we will discuss later, will only be resident. Those portions which are active at a given time, those portions of the program which are active at a given time will actually be resident in the main memory. So, the entire code and data of the process need not be resident in the main memory together. So, the virtual address space of a program can be much larger or arbitrarily large and has no relation with the size of the main memory. The virtual address space can be larger or smaller compared to the main memory that we have. Now, how do we do this mapping from virtual to physical addresses? So, both the virtual and physical both the virtual and physical memory. So, the virtual memory and the physical memory are broken into blocks of the same size, and this block, so the blocks are of the same size. As for caches, we divide into blocks and lines. For virtual memories and physical memories, we divide virtual memory into blocks called pages and the physical memory into blocks of the same size called page frames. Now, the virtual memory translation miss is called a page fault. That means, during translation I have my CPU asked for data corresponding to a virtual address. Now, how do I get that data? I do the mapping so that I find out the corresponding physical memory location in which this virtual data corresponding to this virtual address reside. Now, when I am trying to do this mapping, I am seeing that the page, the corresponding page in physical memory corresponding to the virtual page that I need is not there in physical memory currently. Now, that has to be brought from secondary memory or disk. Now, this constitutes a page fault. When the page that I require, the virtual page that I require is not there in main memory, in a page frame of the main memory, I have a page fault. Here in this figure, we see that we have virtual addresses on one side. These are the virtual addresses. Each of them is a virtual page. These are pages. Now, the white pages, these I have a mapping for them in the physical memory. So, I have a mapping for them in the physical memory. So, corresponding to this page, I have this the content of this page is in the physical memory, this page frame. This, for this virtual page, I have the content in this page frame. However, for this page, I do not have a corresponding mapping in the physical memory. That means, this page is currently not resident in a physical memory page frame. So, what happens? This, when I access this virtual page, I have a page fault and I have to bring this page from the disk to physical memory, and only then can the data or the code that I need corresponding to this page can be accessed. So, I have to service the page fault, and only then can the data corresponding to the page which is not resident in main memory be accessed. So, and the other point is that pages can be shared by multiple virtual addresses. So, the same physical memory page can be mapped, can be pointed to by multiple virtual addresses. For example, in this case here, this virtual page and this virtual page points to the same physical page frame, this one. Now, when is this important? So, there could be code or data which is accessed or shared by multiple programs, say. For example, let us say we have a dynamic linked libraries which are shared files in the system, or let us say we have a language library, say our printf program. Now, all C programs may need to use this printf. There are two options for this. Now, each program can have a copy, each process can include a copy of the printf program into its virtual address space. We will have a mapping of this printf program into its virtual address space. So, program 1, C program 1 and C program 2 both access the same printf program. Now, they can, if it is the same printf program, it is better to share the code instead of each program having a separate copy of that printf program. So, therefore, this is done through a mechanism called dynamic binding. So, what happens is that for shared libraries, you do not actually load the libraries as part of the address space in your executable code. Instead, you just include a stub saying that printf is a shared library which I may need to access from a part of the program. Now, when this shared library is first accessed during execution, I first check whether this shared library is already existent in main memory or not. If it is existent in main memory, I just include another link to this shared library code instead of having a separate copy of it. So, although I bring for the first time I bring this shared library into the main memory, when another program suppose tries to access the same shared library, then what I will do? I will not bring the copy from the secondary memory to storage. I will not bring another copy of the print function of the shared library from secondary memory to storage. I will reuse the same code that I already have in main memory. I will just link from the other program that the printf code exists in this part of the main memory instead of copying, having another copy of this shared library. So, how will I achieve this? I will achieve this by having multiple virtual pages to point to the same physical page frame. So, let us say this physical page frame here contains the code for the shared library. So, now this shared library can be accessed by now, and let us say this virtual page is corresponding to program 1 and this virtual page is corresponding to program 2. Therefore, when both these pages point to the same shared library code, this can be done by what? By having these two pages point to the same page frame here in main memory. So, physical pages therefore can be shared by having multiple virtual addresses point to the same physical address. Virtual to physical page mapping simplifies loading by providing relocation. As we have seen in a virtually managed memory system, the location in the virtual memory is with respect to the start of the virtual page location. Now, these virtual pages can be located anywhere in physical memory. So, therefore, if I have provided an address and I know the start of the page in main memory, I can locate it. So, therefore, it simplifies loading of the program. So, the program can be loaded anywhere into the physical memory, there is no restriction. The virtual pages need not even be contiguous. So, the virtual pages can be mapped by themselves without relation to other pages at any portion of the physical memory. Logically speaking, there are restrictions which we will not go to at this point in time. However, we can assume here that any virtual page can be mapped to any physical page frame. So, allows virtual pages to be mapped to different memory page frames. So, this is relocation. So, in my virtual address space, my code was contiguous one after the another, virtual page 1 followed by virtual page 2 followed by virtual page 3. However, virtual page 1 can reside in, let us say, page frame number 10, and virtual page 3 can reside in page frame number 1. There is no issue that because this virtual page frame was, because virtual page number 3 was after virtual page number 2, virtual page number 2, because virtual page number 3 was after virtual page number 2, it need not be that in the physical page frame also it will reside in physical page frame number 2 followed by physical page frame number 3. It need not be so. So, virtual page number 3 can very well reside in physical page number 1, and virtual page number 2 can very well reside in physical page number 10, no problems. So, programs therefore can be loaded anywhere in physical memory, and this translation also eliminates the need to find a contiguous block of memory to allocate a program. So, if we did not have such a paged memory system where I have the same page size, I have broken both the physical memory and the virtual memory into pages of the same size. If I did not have a system like that, then what would I have to do? When I have to place a process in main memory, I have to find out appropriate amount of contiguous block of memory for this process in main memory. Otherwise, I cannot place this entire process in main memory. Now, I need to only find whether I have free page frames for a given virtual page which is being accessed by the CPU. I have a virtual page which is being accessed by the CPU. If it is currently not there in a main memory page frame, I just need to find or replace a page frame in the main memory, find a given page frame corresponding to this virtual page which I need, place my data from the secondary storage into this page frame, and then access the data after that. So, virtual to physical address translation. A logical address generated by the CPU is broken into a virtual page number and a page offset. So, here I said that let us say I have a 32-bit address space, 32-bit address bus, so and I have a 32-bit virtual address space. So, my virtual addresses will be of length 32 bits. In this figure, we see that the virtual address, or also called the logical address, is broken into two parts: the virtual page number and the page offset. So, the higher order 31 to 12, these 20 bits I am using for the virtual page number, and these 11 to 0, these 12 bits I am using for the page offset. The number of bits in the page offset determines the page size. So, here because I have used 12 bits in the page offset, the maximum number of bytes or words in my page can be 2 to the power 12. Okay. So, I have 4 KB pages in this organization. Now, the page offset is translated as it is, because so this portion, this part of the address tells me which byte within this page do I require, and this is translated as it is in the main memory. This does not change. The virtual page number, this part now goes through a translation, process, and for that I generate a physical page number. So, my CPU has generated virtual address. My CPU, let us say my CPU has asked for a data from a virtual address which is given by this 32 bits. Then this 32 bits is broken into two parts. The lower order 12 bits here forms the page offset, and it tells me which byte this address, these bits, the values of these bits tells me which byte within my page do I need to access at this current time. The higher order bits from the 12 to 31, these bits tell me the virtual page number. So, how many virtual pages can I have? I can have 2 to the power 20 pages, because this 12 to 31 means I have 20 bits for the virtual page number. So, the number of virtual pages can be 2 to the power 20. Now, each of these virtual pages can potentially be translated to a physical page number. Now, for this virtual page number, I will have a corresponding physical page number. We see that the number of bits in this virtual address and this physical address are different. So, this virtual address has 20 bits, however, the physical address we see it is from 12 to 29. So, it has 18 bits. So, so the number of physical memory page frames here is only 2 to the power 18, but the number of virtual pages that I can have for this process is 2 to the power 20. Okay. Now, this one is the physical address. So, this whole thing will be floated after translation, will be floated onto the memory address register. So, the page offset part, these bits will be just placed as it is in the physical memory address. This physical page number, these bits will go through a translation, and this 20 bit address will be transformed to a corresponding 18 bit address after the translation, and after the translation we will together add up this physical page number and this page offset to get the entire physical physical address. This is the frame address, and this is the byte within the page frame that I require. This is the byte within the page frame that I require, and this is the frame address. So, in this figure, the virtual address space is of 2 to the power 32, because I have 2 to the power 32, I have 2 to the power 32 different addressable locations in the virtual memory. The physical address space is of 2 to the power 30 from 0 to 29. So, the size of the physical memory is 1 GB, the size of the virtual memory is 4 GB. The page size is 2 to the power 12, which is 4 KB, 2 to the power 10 is 1 KB. So, 10 bits 1 KB and 2 bits more, so 4 KBs. And the number of virtual pages, as we discussed, is 2 to the power 20, and the number of physical pages is 2 to the power 20, number of physical pages is 2 to the power 18. So, more virtual pages than physical pages is the basis of the illusion of an essentially unbounded amount of virtual memory. Now, the virtual memory can be as big as the address bus that I have. If I have a 64 bit address bus in a 64 bit computer, then the number of the virtual address space can be as large as 2 to the power 64. So, essentially I have unbounded amount of memory. However, the translation process guarantees that all these virtual pages or virtual addresses will be correctly mapped to proper locations in the physical memory. Now, page, as I told that if for a corresponding virtual page number, the physical page is not, there is not a proper translation of the virtual page to a physical page, I have a page fault. What does that mean? I have floated a virtual address, for that I have a virtual page number. The translation told me that corresponding to that virtual page number, this virtual page does not currently reside in physical memory. So, I have to access the data, corresponding data or code corresponding to this page. I have to first bring this page from the secondary storage to a page frame in physical memory, and then I will get a proper translation, and after that can I access data in that physical page frame. So, when I do not have the data in the physical page corresponding to a virtual address, I have a page fault. Now, page faults can be the page fault penalty for virtual memories is very high. Why? Because the access times on the secondary storage is very high. Now, to access whereas let us say for accessing the main memory I will only take around say 50 to 70 nanoseconds, for accessing the secondary storage I may take millions of nanoseconds. For example, it could be as big as 5 million nanoseconds, let us say. So, therefore, to access the secondary storage to service a page fault, I need to access the secondary storage to fetch a page from the disk, and this takes millions of clock cycles. The main memory latency is about a million times quicker. The main memory latency is about a million times quicker than a disk. Okay. So, this amounts to a huge miss penalty. So, therefore, a lot of effort has gone into trying to reduce misses. So, what are the kinds of efforts that has gone into? Now, the first one is that the page size that we decide, like we have to decide what should be the size of a block of cache. Similarly, we have to decide what should be the size of a page. Now, page sizes should be large enough to amortize the high cost of accessing the secondary storage. So, once I access the secondary storage, I need to bring a lot of data together to maximize locality of reference as much as possible. So, if I bring a big sized page from the secondary storage, the probability is that for further accesses the data, if the data is clustered around the address that I currently fetched, then subsequent accesses will not result in page faults if the page size is big. Also, the other part is that when for magnetic disks, for example, secondary storage, the access times for numerous accesses is much larger than if I have a bigger contiguous access of data, bigger contiguous access of a significant amount of data. If I have, that is much better than having multiple numerous accesses to smaller amounts of data due to the organization of the secondary storage. So, therefore, both these aspects lead to the conclusion that the page sizes should be large. Typically, today page sizes are of the order of 4 kbs to 16 kbs. The newer trends for desktops and servers are that it is going to be still higher to even say 32 kbs or 64 kbs. So, each page will be of size say 32 kbs or 64 kbs. Why? In order to reduce the number of times I need to go to the secondary storage to access access data. So, once I go to the secondary storage, I want to bring a lot of data together, so that further accesses for further accesses of data, the probability that I have to go to the secondary storage is minimized. The probability of a page fault is minimized. However, for embedded systems, page sizes are typically lower of the order of 1 KB. This is one reason for this is that could be that embedded systems are resource constrained. So, their memories are lower, and bigger the page sizes, bigger becomes the internal fragmentation of the last page. Suppose for example, I have page sizes of 4 KB and I 4 KB and I have say and I have a process whose virtual address space whose virtual address space is of size 18 KB. So, I will require 5 pages, 4 KB, 5 pages, right, but in the last KB 2 KB in the last page 2 KB of space will be wasted, because I require only 18 KB, 2 KB of space will be wasted. This amounts to internal fragmentation, and many embedded systems may not afford such internal fragmentation. So, and also because for embedded systems the processes that are executing and their memory accesses are much more predictable, I can have more efficient ways of managing memory in embedded systems, because the exact processes that will be run are typically known. This is not so for desktops and servers. Arbitrary processes can come at any point in time and execute. So, in resource constrained embedded systems, page sizes are typically lower. Organizations that reduce page fault rates are also attractive. So, CPU system organizations that reduce page fault rates are also attractive in virtual memory managed systems. So, virtual memories are typically use fully associative placement of pages in main memory. Now, for caches we saw that the principal there were two principal problems of having fully associative caches. One was that I needed more expensive hardware to search for the tags, to search for a tag match which has to be done in parallel. Okay, because a particular physical memory block can reside in any cache line. So, I have to check for the tags of all the cache lines to find out where my data exists. So, this made it very expensive for cache memories. The other way, the other problem was that when I needed a replacement, how to find which page to replace. To find, let us say, the LRU page, the least recently, which block to replace. To find the least recently used block, I will need very expensive hardware to keep track of which page is least recently used at a given time. So, we used typically use set associative mapping for caches. Now, for virtual memories, on the other hand, associative placement is more beneficial. Why is it more beneficial? Because the access times to the secondary storage is very large. Now, so what I want to minimize page faults, I need I want the a virtual page to I want a virtual page to I want to be able to map a virtual page to any place within the physical memory, to any page frame within the physical memory wherever possible, because that minimizes my misses, page faults. Now, this is much lower. Now, what is the drawback of this approach? The search of where a virtual page exists in the physical memory becomes higher, but this search is much lower in cost in comparison to the cost of a page fault. Hence, the fully associative placement of pages in memory are preferred for virtual memories. And page faults are handled by the OS code and not hardware. Now, why is this so? Because so this is being done in software. So, again this will be more costly as compared to hardware. However, because page faults are very expensive, compared to that compared to that handling page faults in software is much lower in cost. In addition to this, when I handle page faults in software, smart replacement algorithms can be used to reduce cache misses. We will look at different replacement algorithms and how such replacement algorithms helps reduce not cache misses, page faults. So, smart replacement algorithms can be used to reduce page faults, and we will see how the replacement algorithms help reduce page faults. And obviously, the last point here says that write-back caches are write-back mechanism is used for in virtual memories and not write-through, which means that suppose when I write onto a physical memory, I do not write to the corresponding location in virtual memory or the secondary storage. I use a write back scheme, because if I go on each time I write into physical memory, if I have to write into secondary storage, it will be hugely costly, as we understand. So, write throughs cannot be used, write back is used. So, whenever the page needs to be replaced, modified pages will be replaced, and if the page is dirty or modified is written to, when it is being replaced, it will be placed into the secondary storage, and we will not use write through, because as we understand, write through will be very costly. In write through, for each write into the physical memory, I must also write into the secondary storage, which is not possible, affordable at all. Now, we look in more details as to how virtual address to physical address translation is done. This translation is done through a data structure called page tables. So, page table stores placement information. It has an array of page table entries indexed by virtual page number. So, for each process, I will have a page table. This page table will have, these are virtual page which will have entries for each virtual page. So, virtual page number 0, 1, 2, 3, 4. So, these are virtual pages. Corresponding to each virtual page, the page table will contain the corresponding physical page frame number. Physical page frame number. Okay. So, page tables store the placement information. It is an array of page table entries. It is an array of page table entries indexed by virtual page number. So, the index is the virtual page number, and it contains what? The physical page number. So, page table registers in CPU stores in CPU points to the page table in physical memory. So, when I have a context switch, what do I do? During a context switch, a new process is executed on the processor. During that context switch, for each process I will also have a page table which maps what? Its virtual pages to its physical pages. This physical this page table is also resident in main memory. Now, the page table register is a hardware register which during a context switch is populated with the address of the starting address, which is populated with the starting address of the page table in physical memory. So, again page table is an array of page table entries. It is a data structure which is there per process. Every process has its own page table. Page table maps the virtual pages corresponding to that process to corresponding physical pages. Okay. Page table is an array which is indexed by virtual page number, and the page table register is a hardware register which contains the address of the start of the page table. So, the address of the start of the page table in physical memory is kept in the page table register. So, the data corresponding to this process and also the data code of this process is in physical memory, and the page table of this process which maps virtual page numbers to physical page number, this is also kept in the physical memory. So, and there is a distinct or its own, each process has its own page table. So, during a context switch, what do? I populate this hardware page table register with the address, with the starting address of my page table, of this processor's page table which has come to the processor subsequent to the context switch. The starting address of this page table is put into the page table register. Okay. If a page is present in memory, PTE stores the physical page number, and it can stores other bits such as reference bits, dirty bits, etc. So, we will talk about all this later. Reference bits are used to understand whether this page was referenced within a given time in the past. So, I have different time epochs, and within a given time interval, if within a particular specified time interval, if my page was accessed from particular time interval from the current time to the past, within a given time in the past interval, if my page was accessed, my reference bit will be 1, otherwise my reference bit will be 0. Why that is used will come later. The dirty or modified bit is used to understand, whether this page was written to or not. Why is this required? As I said, this virtual memories are write back. So, if I find that the dirty bit is on and I want to replace this page, then what do I need to do? I have to, if this page is dirty, then I have to write it back into the secondary storage. Okay. So, we will look at these later in more details. If a page is not present in memory, this will be a page fault. The page table entry can refer to location in swap space. So, I have to go to the swap space in disk, on the disk, and bring back this page. So, the swap space is something called, as we know in Linux, you must have heard the term swap partition. This swap partition is basically the swap space that we are talking about. Why this is there? The swap space typically contains the portions, the data portions of each process which are dynamically changing. The code part which will never change, the code of the process is never going, the code of the processes is never going to change, that is typically kept in the other part of the secondary memory along with the process. The data which will be frequently changed is put in a special partition, in a special small marked area within the secondary storage, which we call the swap space on the disk. So, as I said, each process has its own page table, and this maps its virtual address into the physical memory. So, here this is the page table of process 1, this is the page table of process 2, and we see that the pages are mapped to corresponding page frames in the physical memory, and the physical memory is nicely shared between this process 1 and process 2. A few of the page frames contain data corresponding to process 1, other page frames contain data corresponding to process 2. Okay. This figure shows how nicely the physical memory is being shared by two processes through their own page tables. Now, we will see how this translation occurs. So, now this is with respect to a single process. So, I have a single page table register, there is a single page table register, This page table register contains what? It contains the start or starting address of my page table in physical memory. Okay. So, now what happens? The CPU, when this context switch was done, this page table register was populated with the address of the starting address of my page table. So, now I can access my page table, I can access this page table. Now, the CPU, the program is running, the CPU has generated an address for a, let us say, for a given data, and that address is a virtual address. So, this is my virtual address. Now, this virtual address will be mapped, the offset part will be directly used in the physical address as well. The offset part of the virtual address will be directly used in the physical address as well without no modification. Now, I have this 20-bit virtual page number. Let us say, now for each entry in this, for each entry 2 to the power 20, there are 2 to the power 20 different virtual pages. For each virtual page, I will have an entry in the page table. So, what will be the length of my page table? My page table will have 2 to the power 20 entries. Page table will have 2 to the power 20 entries. Okay, we will have 2 to the power 20 entries. Now, let us say corresponding to this virtual page number, these 20 bits, this is the index and this is the physical page number. From the valid bit, I have found that what I have found that this mapping is valid, which means that corresponding to this virtual page number, this physical page number is actually valid. The data corresponding to this virtual number actually resides in this physical page number. If this valid bit was off, it means that this page number corresponding to this virtual page number, this physical page is not there in physical memory. So, I will have a page fault. If this is off, I will have a page fault. Now, if this is on, let us say this is on, then what happens? For this virtual page number, I will get the physical address, physical page number. This physical page number is of 18 bits and I get the higher order 18 bits of my physical address. Okay. And I also get the page offset. I add this up together and get my 30-bit physical address. Okay. So, the page table of each process is also stored in main memory. A hardware register called page table register is used to locate start of the page table for a process. The valid bit for each entry indicates whether the mapping is legal. If the bit is off, the page is not present in memory, main memory. Although a page table entry needs only 19 bits here. Why do we need only 19 bits here? I have 18 bits are required for my physical page number and one valid bit. So, in this case I require only 19 bits. However, I typically round it to 32 bits for ease of indexing. Okay. So, I typically round it to the next power of 2 for ease of indexing, because I work with bits, I can break addresses and I can do many things. So, however, although I waste a certain number of bits in my page table entries, I still round it up to 32 bits. These extra bits, however, are in many times used for many to keep many types of additional information. For example, protection information. So, for example, for a given particular virtual page, I know whether this virtual page contains a program's code or the program's data. If it is a program's code, I can keep an additional bit to say that this part is read only. I should not be able to modify this part of my this part of my data. So, if this is a code, then I should not modify the corresponding content in my main memory corresponding to this virtual page. So, that information I can keep. So, even if the CPU tries to modify the data, I will say that this is an invalid operation based on protection bits. Similarly, I can keep read, write, execute bits different other protection bits corresponding to using these free bits that I have that are unused. Okay. So, additional information can be used for in these bits on a per page basis. For each page I can keep separate protection bits. So, I can use it in this way. With this we come to the end of this lecture.